Yeah, thank you very much. So I'm going to be talking about decoding error correction experiments run on the device discussed in the previous talk, and in particular looking at the effect of including soft readout information in the decoding process. As Hanny mentioned in the previous talk, the experiment we're considering is the Surface 13 experiment, which is a quantum memory experiment for the distance 3 surface code, but only measuring the Z stabilizers. We prepare the data qubits in one of the 16 basis states that make up the full logical 0 state, perform syndrome extraction for some number of rounds, and measure the ancilla qubits at the end of each round. One thing to note here that I'll come back to later is that we don't reset the ancilla qubits between rounds of syndrome extraction. At the end of the experiment, we measure the data qubits. And from these, we can construct the uncorrected logical measurement. As is typical in error correction experiments, we define detectors, which are combinations of measurements that we expect to have deterministic values when there are no errors occurring. For a particular run of the experiment, we then evaluate or record the defects, which are the detectors that have changed value. We pass those defects into the decoder, which has also taken in a model of the errors. It uses these to work out what errors have occurred and whether we need a correction to the logical operator, which finally, combined with the uncorrected logical measurement, gives us our final logical measurement. So before I talk more about the different decoding techniques we used in this work, I'm just going to touch on how we perform measurement classification in this experiment. The readout signal is integrated in two parts, the in-phase and in quadrature components to give the I and Q voltages shown on the X and Y axes on this figure on the left here. This is calibration data for a particular qubit prepared in a particular state, and then the IQ voltages read out. And we use this calibration data then to classify the measurements during the course of the experiment. We first find it convenient to project the voltages into just a single component along this horizontal line here to give the figure on the right-hand side where the Y value is showing the probability density as a function of the projected voltage for the two states 0 and 1. Then to determine our particular measurement, we simply classify based on which side of this vertical line the projected voltage falls. This projected voltage is what we'll call the soft readout information for the rest of the talk, and the 0 or 1 measurements are what we call the hard readout information. So typically when decoding, you just pass in this hard information, but as you can imagine, there is information within the soft information that can be useful to the decoder. So this 2021 paper proposed using this soft information in the decoding process, and what they find in some simulations is that this improves your logical performance. So the y-axis here is the logical error probability per round, and the solid lines are decoding just using hard information. And we see an improvement moving to the dashed lines when we include soft information in the decoder. Furthermore, in this 2023 paper, the improvement using soft information in decoding was also observed in a real experiment, moving from, I think, the green dots down to the silver dots is an improvement in the logical error probability when including the soft information. So in this work, we're also looking at comparing decoding using just hard information and soft information. And in particular, we're focused on decoders which learn their model of the errors that can occur from the error correction experimental data itself. And we look at two decoders, a minimum weight perfect matching decoder and a neural network decoder. Minimum weight perfect matching decoders take as their model of the errors that can occur a graph, where an example of which is shown here, where the nodes correspond to detectors, each edge corresponds to an error, and the nodes at either end of the edge are the defects that would occur if that error occurs. Each edge also has a weight associated with it, corresponding to the probability of that error occurring. So this graph here is for a surface 13 experiment if we were resetting the ancilla qubits. As I mentioned earlier, we don't reset the ancilla qubits between measurements, and so we get this graph with some additional edges in it. In order to obtain the weights for the edges in the decoding graph, we use a pairwise correlation method, which uses the experimental data itself, the observed frequencies of the defects occurring, to construct the edge weights following these papers down here. So for our hard minimum weight perfect matching decoder, we use exactly the graph generated using this method. For the soft minimum weight perfect matching decoder, we update the edge weights for each run of the experiment following the paper that introduced soft information decoding. So the edges that correspond to measurement classification errors should have their weights updated based on the soft information. In the bulk of the experiment, we can simply do this by replacing the edge weight of these green edges with the one due to the soft information. In the final round of the experiment, both classification errors on both the ancilla qubits and the data qubits don't lead to sort of their own edges. They're also in edges where qubit errors also form part of the edge. And so we don't want to totally replace the edge weight we got from the pairwise correlation method. We instead remove the average classification error and then per shot add in the soft, the contribution due to the soft information. Our second decoder is a neural network decoder based on this paper here. And again, we have both soft and hard variants. The hard variant takes just the observed defects as inputs. The soft variant also takes in the bulk of the experiment, the probabilities of the defects occurring given the soft measurement outcomes. And it also takes in leakage flags. So we can look at measurement calibration data, not just considering the 0 and 1 states of the transmon, but also considering the possibility it's leaked out of the qubit subspace to classify the measurement to 0, 1, or 2. And the soft neural network decoder also takes into account this leakage information. So finally, our results are here with the minimum weight perfect matching decoder on the left, the neural network decoder on the right. In both cases, on the x-axis, we have the number of rounds in the quantum memory experiment, and on the y-axis, we're showing the logical fidelity, so the proportion of the time that the corrected logical measurement is correct. And what we can see in both cases is that the decoder using just the hard information, in both cases the blue line, performs slightly worse than the decoders using the soft information, the orange lines. And so we have obtained an improvement in the logical performance using the soft information. We also extract the logical error rate by fitting this function, a measure of the performance per round, and we find that overall the best performing decoder is the soft neural network decoder. So just to end on a brief summary, we have run the Surface 13 quantum memory experiment on real device without ancilla reset. We've explored decoding using a minimum weight perfect matching decoder and a neural network decoder, both of which learned their models of the errors from the experimental data itself. We looked at hard and soft variants of the decoders and observed an improvement when using soft information. Thank you.
All right, so we're still running a couple minutes behind. We have enough time for 1 or 2 questions. Okay, nobody's biting. Chair's privilege. So if a T1 decay occurs on an ancilla while you're reading it out, the signal depends on when the decay occurred, but the signal that you wish you had measured and the state of the qubit at the end don't. So is there a way to use the whole time trace to squeeze more soft information out rather than using the integrated trace?
Yeah, that's a great point. We do just integrate across the whole time. As you say, there's even more information in there which could be used to identify that kind of thing. So one thing we do is try to distinguish. So we would view, say, a T1 decay from the 1 to the 0 state during measurement as a qubit error rather than classification error. So we try to sort of separate those two processes out. But I think, yeah, you're absolutely right. And I think there might be some work on, looking at, actually, there's much more information in these non-integrated traces and including that.
One more? No? All right, with that, let's thank Ophelia again.